coming from the University of Edinburgh, where he is the director of the Institute of Perception, Action and Behavior. He also holds a UK area Turing AI World Leading Researcher Fellowship. Keep it short, and over to you. Thank you.
Thank you very much. Thank you for the invitation to this excellent event. I've enjoyed it so far. So I'm going to tell you a little bit. So when I first was invited, and then I looked at the schedule and I realized I'm the first speaker after lunch. You know, I thought like people are going to be a little bit switched off, and I should say something controversial. But then what I was going to say maybe isn't so controversial given what other people have said, which is that although we talk about things like world models and foundation models and so on as a brand new thing, to somebody trained in engineering and control, models are what we've always been used to. So it's not like it's an entirely new thing. So the way I'm going to structure my talk is I'm going to say a little bit about a number of different projects that we are working on. I'll begin with asking certain questions about the most recent emergent models with kind of big data and so on. But then my focus will be on saying what do I think they're missing and how might we want to go about them with respect to things that I'm interested in my applications. So let me start by kind of, asking a question with respect to a famous robot. This is a robot that many of you have seen, heard about. And I like this particular demo from Boston Dynamics quite a bit because it's not just one thing. This robot, it's a very scripted demo for sure, but it's a nicely scripted demo where the robot's doing lots of different things. This guy has supposedly asked for help through his app. The robot decides it needs to get up there. It doesn't quite know how to get there. Then it finds this plank, puts it there. And what you'll soon see is it's now created a path for itself. So it's going to go all the way up there. And the whole purpose of this exercise was to carry that bag up to him. Now we can sit here and debate, will this actually happen? Will you spend $2.5 million to get a bag up there to this guy? That's not the question. The question is, if this is the kind of robot you're building, what kind of models do we need? It's not immediately obvious, right? So we are all excited by the fact that, look, language has been revolutionized. But the kinds of structures that work well for language, even for vision, I would argue, are perhaps somewhat different from what the structure is here, because we can't quite pin down and say, what is the structure we're talking about? Is it the controller? Is it the planner? Is it the interaction? What is it, right? So that's kind of like just the teaser at the start to set up some of the questions I'll be asking. So the first section I want to talk about is, okay, then what is the role of big data in robotics? We're all excited by the fact that many fields are beginning to be revolutionized. The hope, and one of the reasons why we have workshops like this, is that maybe a similar story will play out for robotics. And the story is that if you have a sufficient corpus of data, which is sufficiently representative and broad coverage, you might be able to train generalist models, which can then be fine-tuned for a number of different applications. The reasons this might be hard, which many people have already alluded to this morning, is that firstly, there isn't an internet of robot data. There is no common crawl that you can just go around and say, I've got like this giant corpus from which I can just learn sequences. And collecting a lot of new data is extremely tedious, as any of us who's done physical robots would know. And then there's the usual problems that robotics data is slightly different from the kind of discrete tokens that language naturally presents itself in. So perhaps one of the first things that we need to do as a community is to start collecting a lot of this data. So I'll start by saying some things that we've done in this area. We got involved about a year and a half ago in a large consortium effort, which was led by people, among others, from Google DeepMind. So it's a shame Francesco isn't here because he might tell me a lot more about what's going on in this. But there's been a big exercise sort of across the world with many partners, in multiple countries that have come together and said, let's start collecting the equivalent of Common Crawl. And the way we did this for this particular data set is that there was an agreement about a certain robot platform. It's a Panda robot with Z cameras. You put them together. And then everybody went out and for a year collected volunteers and collected a lot of data. And as you can see, it's representative of lots of different scenarios. And what that gave us is some reasonable coverage of kinds of environments, kinds of tasks, kinds of concepts you might want to get, and some diversity in terms of is it industrial, is it domestic, and so on and so forth. So you have let's say, the beginnings of kind of interesting data. And what that allows you to do is just, in the abstract, is that if you didn't have that much data versus if you had that much data, then depending on what metric you use and what task you use, it does much better. And this has now become part of an even larger project called Open Cross Embodiment, which kind of feeds into the RTX class of models that Francesco was talking about in the morning. And what's nice about this even larger kind of data set of data sets is that we have multiple robots, multiple environments, multiple tasks, and we're kind of beginning to fill in that matrix. And that's what then unlocks variety of these models that are now beginning to give us these exciting possibilities like, I haven't seen this house before, I haven't seen this robot before, can I instruct it? So this is exciting, and this suggests that there's a lot of promise in thinking in a data-driven way. But having said that as a preamble, for the rest of my talk, I'm going to kind of say, why might this not be enough? And I'm going to kind of spend a little bit of time, digging into the details a little bit of things that don't quite seem to work out for us. So the first thing I'm going to pick, now I'm a professor of robot learning, and for me, robot comes first and learning comes second. And what I mean by that is, I derive my questions from saying, what would I like my robot to do? And then I look for learning and adaptation mechanisms that facilitate it, rather than going the other way around. There are many ways of doing research, and this is how we do it. And what that means is sometimes we are looking at domains. In this particular project, we were looking at assistive use cases. Many people in the audience do the same thing. And then we asked the question, what are the things that we do on a daily basis, and why might they be hard? So here's one task, which is you want to manipulate cloth. This is a pillow cover. If you woke up in the morning and made your bed, you did something like this. This is slightly different from the usual presentation you see because it's in-air manipulation where the cloth is just hanging in air and you do the slightest thing and it moves off. So it's not a fixed thing that kind of presents itself. And then the cloth comes to you in various shapes and sizes, various specifications of exactly what you need to figure out about its edges. So it's this diversity between the presentations of shapes, presentations of how the crumple presents itself, the visual appearance, all of these things put together that you're trying to cope with in a dynamic sense where things move all the time, right? Now, there are a number of standard architectures that one could use. Here we started out with an architecture called Dreamer, and there's many variants on Dreamer that people have been exploring within robotics. And off the shelf, it doesn't really work in our setup. For a variety of reasons having to do with the fact that it's dynamic. So we had to make lots of modifications, starting with the fact that we really needed some understanding of depth, without which just from pure vision, it doesn't do a whole lot. And then having done that, we need to think very carefully about the structure of how the replay buffer presents itself, what data you need for the world model. So again, just the raw data that you get from large data sets was not sufficient, and we had to kind of carefully structure the ways in which you do domain randomization and the kinds of demonstration that we can give, such that it had sufficient coverage to then take on the wide variety of garments that we were interested in, the wide variety of other variations to this task. And then that allows us to get to the point when it can do what, when I show this to my family who don't think much about robotics, they're like, come on, this is not much of a task, is it? But actually, like, this is pretty difficult for us as robotics people in the room know. What does this give us? I mean, there's a lot of numbers, you don't need to go through them all. The game when one of us presents a table like this is that we are basically saying that our method does very well on a variety of presentations of garment types and what's going on here. So what do I want to say with this? The point is that even when we have a lot of data, when you're trying to present it in a closed loop embodied system, you still have to think a little bit carefully about the individual details. And it's not quite as automatic as one might kind of naively hope for. But then I think the story gets even more interesting by the time you ask this question, which is something that has occupied my attention for the past few years and something I'm beginning to think about more and more, which is that when we talk about world models, we're often thinking in terms of objects, object manipulation, and things like that. Where are people in all of this? And what is the meaning of people when it comes to predicting people? And so let me give you one example. And this is a project that we did a few years ago now. And the aim of this project was we were trying to understand handover behavior. So here's my student Paula, and we had a peer too. And at the time, we were beginning to work with a cohort of people who had sensory motor disabilities. So they couldn't quite move in certain ways. An example of a disability might be that I can't really use my right hand well, or I can't extend my hand, I can't do certain things. Which means that if you were a person who was helping this person, you would very quickly figure out, oh, that means I should hand over like this, or if it's a heavy object, I should hold it in a certain way and not ask you to hold this. So there's a lot of subtlety to what is a very seemingly simple behavior, which is just handover. Normally in robotics, when we say handover, you give the object, there's some space, the robot grabs it or the person grabs it, and job done. But in this case, we are saying, no, it's not just about doing that. There's a lot more subtlety to what's going on with these objects. How would you figure this out? And much more importantly, how would you figure it out for this one person? Not a mythical averaged person, but for this one person, how do we figure this out? So we built a stack, and I'm not going to describe the full stack here. For the purposes of what I'm trying to say here, what's interesting, I think, is that there's a combination between motion planning concerns, which is sort of where should a robot grasp, and then how does the grasping problem work? And this is something that many of us understand. You've seen lots of examples. And then there's the question of, if you are going to use this for something, if the person's going to use this comb to comb their hair, how should I present it to them? Well, you want to make it such that the person gets the handle. And then if that's what I want to do, maybe I should hold it here. And then if they can't quite grab it well, then I have to present it like this. If they're perfectly able, then maybe it's more polite to present it like this, and so on and so forth. At the time, the way in which we approached this was that all the low-level processing in this is done with sub-symbolic architectures. We had a neural network that does kind of the object understanding and segmentation and all of this. And then the control is done with an optimization-based framework that's also like that. But a lot of the kind of subtle reasoning about what makes sense was at the time done with a Markov logic network, which allowed us to do a statistical relational learning approach to this. And what that really says is, there's a number of features here. If it's a person who has these kinds of needs, if it's this kind of a task, and if I have this kind of an object, this is how it relates to each other. So for the purposes of what we're discussing here, where does this live inside our large models? Does it live inside a reasoning engine? Is it part of a big data set? And it's not quite clear to me exactly where this goes into our modeling framework, but we need it somewhere. The second example that I want to use in this subsection is a different form of close interaction, which is that I'm quite interested in applications where we have manipulation of soft objects. Now here's another example from daily life. Breakfast, you probably manipulated some soft object like this. The question is, what did you exactly do at the control level such that I can get my robot to do the same thing? What's interesting about this task is that there's a soft material sitting inside a hard material. There's an interface. The control problem is defined by carefully gliding on that interface. What people do is that they have expectations and predictions about tactile forces. So in world model sense, they have a world model in this tactile space. And then somehow they're doing sensible proportional corrections to it. Why is this an interesting task? Because this is kind of step one of a big ladder of tasks that we'd like to solve, because we're working with people such as surgeons, and we're thinking about automation in the context of medical robotics. And if you want to kind of climb this ladder, then you have to begin to understand what do they do with soft tissue, which is not just a control problem. It's not just, how do I move my object, but what do they do with respect to this object such that it gives you the effect that it wants. So one canonical task for them is this one. So I want to excise a lesion that's on your skin, and you take a scalpel and then you kind of cut it out just so. It's a control problem because you have to manipulate your forces just right, but it's also a planning problem in terms of you don't want to do the wrong thing. So how did we approach it? We had a cohort of trainees and experts who came and gave us data in our lab. We built a customized instrument so that we weren't just getting information off of the edges. We actually had information on what forces were being applied at the tissue tip. And that gave us a corpora of data that gave us force profiles that were being applied with respect to what's going on with the phantom tissue and where we were in the plan of the task, which allowed us to then build generative models, but not in the sense that some of us have been talking about today, but these were generative models in the slightly older sense of their probabilistic generative models. It's a switching dynamical system. And it's a switching dynamical system between the fact that there are dynamical phases when people are doing certain things, which is force control, and then they're switching between them depending on what they needed. If you now take that as an object, and then if you look at an embedding space of the parameters of these models, then what you get is a description that tells you the kind of qualitative features that actually define the task for a good surgeon. So what they're trying to do is they're trying to control between how aggressive they are, how firm they are, what the outcome is with respect to the tissue. So the task is not get rid of the lesion, and I could define a reinforcement learning problem and say get rid of the lesion 1, 0. The task is actually control in this more complex space depending on your subjective view of what you think is expertise, and do that. So the task is actually much more delicate, but then there are models inside which are exactly these models that we've been talking about. And once you have this kind of an understanding, we can try to say, okay, now let's go and try to automate this kind of a behavior on a robot. So I see variation in different ways in which people do it. You could be a complete amateur, you could be an expert, and let's find ways in which we can get the robot to do a similar kind of behavior. So we have an understanding of the feature space, we have an understanding of this difference between expertise and not expertise in this very multidimensional sense. So then we can go through a trajectory optimization process in which we say we're going to change the parameters of your action such that you look more like what they want. And I want to re-emphasize this point here that there's no one universally good way of doing this. In fact, we spoke to multiple experts, and when we sat down with a neurosurgeon and said, what is a good way of doing this elementary task for you? And then we sat down with a plastic surgeon, a reconstructive surgeon, and they both gave us quite different answers. They were both good answers, but they said they're different answers. So this space is very much customized to a person, and then depending on what that customization is, you want to modify what the robot does in order for it to do this task. By the time you scale this to anything like a real operation, you're going to have a lot of this kind of dynamic adaptation that you want to do. But what this allows us to do is to take a landscape, and then given that we have this landscape within the features, we can adapt the trajectory so that we can get different kinds of behaviors. And we can look for, this gives us both a quantification, which is how do you take a student and make them expert, but also how do you take your robot and optimize the robot behavior. We've done the same kinds of things in other domains, such as if you want to automate this skill of searching for a feature when you don't completely know what you're looking for. And then what we've done here again is to take the same learning from demonstration kind of approach, and then saying that we can learn the scan strategies, and then we can go towards automating it such that we can get the robot to perform the same thing. Now I'm kind of whizzing past a few different examples here, but this is all to motivate that for many of us, the problem we are solving is not just a task in the sense that we normally describe it in our papers. The domain is much larger. And the domain is larger in the strict sense of completely specifying what the task is in itself a big research challenge. And so some of us, when we were part of the Trustworthy Autonomous Systems program, wrote a paper in communications of the ACM where we are trying to make this observation that completely specifying what it means to do the full task in kind of obvious domains like assisting a human or driving, it's actually incredibly challenging because you always leave out things that you wish had been specified to an automated system that nobody bothered to specify, right? So if that's the level at which we are talking, then we really need to bring people into the loop much better. And that's the sense in which I was asking, where are the people in our models? And so in a lot of my work, I'm thinking a lot about how do we work with them. And there are two paradigms in which we do it. One paradigm is known to roboticists as learning from demonstration. But every time I've seen somebody talk about it, they apologize for it. They keep saying, oh, I apologize that all I did was LFD, I should have really done AGI. But I'm saying, why apologize? Because the only sensible way in which you can ask questions like the one I'm asking is to fully interact with your human partner and let them drive the learning, not view it as a handicap, right? And then the second sense in which problems are interesting is that we want to work with a human partner in the sense of build autonomy for a collaborative assistive purpose. And here again, there's a lot of history of teleoperation and shared control, but we're asking, what does collaboration in a more intricate sense mean, like cooking together? And for that, we need much richer models of the human skill. So I've given you kind of glimpses of what looks like control skill, but if you build this up all the way to the kinds of skills that we want in the domains we're interested in, then you need to know a lot more. So that brings me to the final section, in which I want to tell you about a few projects that we're looking on, we're working on, in which we're looking at this question of interaction much more directly. And these will be less control rich, and here we are more looking at what does interaction look like in the ways that people seem to normally interact with each other, and then how can we bring that to robotics. So one example is, how do people teach each other? Now, in all the examples I've given, I'm speaking of interaction at a level that doesn't actually happen between people. Even when I kind of learn a skill myself, when I learn to drive or when I learn to play tennis, people didn't sit there for hours on end and move my hand around or kind of move my steering wheel around. That's not the level at which it happened. We got much higher level information, and in a strict sense, the way in which we seem to get information from people is that we use a lot more linguistic structure than we give ourselves credit for when we do machine learning. So when we say label, example, we're kind of going back to old way of thinking about classifiers and restricting ourselves to that representation. Whereas what people actually say to each other is at the level of, oh, if you're trying to distinguish between these glasses, you just have to know that burgundy glasses have this, and so on and so forth. This is not something I know a lot about. So I used to think of all wine glasses as wine glasses until we started looking at ways in which people do this kind of fine-grained classification. But the important thing here is that there's a lot more structure in natural language that normally doesn't present itself when we're talking about classification data sets, for instance. And that structure can actually be utilized, and the way in which you utilize it is that it's a signal. So the way in which the structure is utilized is that you use the generality, the universal quantification of these kind of linguistic constructs as a means of giving much more rich information down to your subsymbolic classifiers. And when you do that, then you get kind of performance benefits. So what you see here are two learning curves in which there's a class of algorithms that do not use this kind of linguistic feedback, and then there are algorithms that do. Now, they're both kind of neural network-based classifiers at the low level. The distinction is that this one has the additional information that came from the linguistic signal that we are able to use. And this is a theme that we've been following much more generally. So we are now looking at ways in which you can have neurosymbolic architectures where you have a reasoning component, where the reasoning component is that you're taking things that come out of language, such as it should always be true that if you have this kind of an object, these things happen. My favorite example these days is we have a 6-year-old who's completely into Lego Ninjago, and I don't know much about Ninjago characters. And literally, I'm sitting there at breakfast and having these conversations, and the ways in which these characters interact and differentiate from each other are extremely subtle. It's that you have to know that this person has this attribute and not that attribute, and the relational structure is quite intricate. But then ultimately what you're doing is saying, is it this guy or is it that guy? You know, do you do this or that? So you need both the underlying visual processing from which you get to objects like seeing graphs, which is a useful intermediary, and then the reasoning process that goes on top of it to say, if you said that all these characters don't have this, I should be able to very quickly do this without needing 1,000 more examples of that type somewhere here. And so that allows us to do things like this. You say, why did you think this is a dump truck? It says, oh, I thought this is this. And no, that's not what it is. And that's very much a human-like kind of feedback. And we want architectures in which you can have conversations like this with your agent, precisely because there are always novel concepts that we don't know about. So to give you one example of a novel concept that I hadn't quite considered until recently, there are many different kinds of apples. And I've slowly come to understand that in Britain we make much more fine-grained classification between apples than I've ever done in my life anywhere else. One example is Granny Smith apples, and at the time we took some of the vision language models that we understood well, and we said, show me Granny Smith apples. And actually it didn't do a very good job at all. It could get us all apples, and it kind of understood pieces of it, like what's the granny. But Granny Smith apple is a particular kind of thing. And kind of there's no reason for these things to do a particularly good job of that. But then you might have situations like you're saying, take the two Granny Smith apples and put them in this left-hand basket and then put everything else in this other basket. Model says, I'm not quite sure. How do you then converse with the model? You're trying to build a capacity wherein it says, okay, then show me what are Granny Smith apples, show me all of them. And then depending on what it does, correct me when I'm not doing the right thing. So you want reasoning at this level of elaboration. And if you do that, and if you build that in just right, what you get is actual performance benefits. So this last agent is the one that we built, which has benefit of this kind of reasoning on top of the neural network architecture. And then the other ones don't do much reasoning except just take it as a binary variable. So this is an example of ways in which we are kind of working together with people at a much closer level in terms of the semantics. So I'm going to conclude by just telling you about something that I've had the privilege of receiving recently, and more for the early career people in this audience. It's a collaboration opportunity if you're so interested. So I've been fortunate to get a fellowship, and this fellowship gives me the resources to set up a new center on AI for assistive autonomy, which brings together all the activity that I've been describing and then allows us to go in a much more ambitious way towards new opportunities. So the way we're going to think about this center is that I have basic science questions I'm interested in, such as, to take my question about, what do you want to do about people? I really want to work much more closely together with psychologists and neuroscientists and try to understand what is it about people? What is it about the loss of memory? What is it about the loss of function? And can we build machine learning models that can represent them in a rich way? Can we then apply them in domains of interest to me? And the domains of interest to me range from kind of care and healthcare to autonomous driving, areas in which I've done some work. And then we're going to structure all of this through assets that we hope become things that other people can use as well, and we can use that as a means to collaborate with people. So we're going to be recruiting in the next few months for postdoctoral positions, PhD positions, and also because I now have the capacity to dedicate all of my time to this, I'm extremely interested in new collaborations and kind of rekindling old ones. So please reach out if you are so interested. And I'll end there. I'm happy to take questions. I'm here for the rest of the day if you want to have a chat, and these are my contact details.
All right, questions for the speaker?
Thanks, Ram. That was great. You talk about sort of neurosymbolic reasoning and symbolic reasoning and so on. Of course, neurosymbolic is something that's recently resurfaced, apparently, as a reinvention of symbolic reasoning. What do you think are the limitations? I think we can all agree that we need some form of that in the current data-driven learning world. But what do you think are the limitations of the current symbolic, neurosymbolic approaches in this context?
Yeah, it's a very good question. There are two that kind of immediately jump out. One is that any connection that I've seen between what works well with big data neural network models and the symbolic layers has been extremely clunky. And they've not been rich enough in the ways that we would like them to be. There are obvious kind of scaling difficulties with the symbolic side if you don't set up everything else well. I think the second one is less salient, because if you do things right, you should not be reasoning at a very fine-grained level, you should be reasoning at a higher level. But the fact that we don't have clean interfaces between the two is, I think, much more of an interesting research question that as a community we should do better.
Can I just add on here?
Yeah.
Isn't the discretization of your representation is a kind of symbol? It's a big symbol in a vector space.
That is true, and that's kind of what I mean, is that if we do that naively, we end up in lands in which the symbolic reasoning is just computationally intractable and you get no benefit at all. So when we say that people do reasoning, I think people do reasoning well because they're very careful about what they reason about, what generalities to keep, what not to keep. And if we don't do that carefully, then we go into a space where actually symbolic reasoning is extremely weak. And it's only if you have the right symbols that it makes sense to reason in that way.
And can I ask second question? So if you agree that like discretization is a symbolic kind of, then why do you need a like symbolic then? Cannot like we learn into like deep learning big models, discretize them, hopefully they will be a kind of symbols. And here you go, you're getting both.
So let me give you this example, right? So when I say things like what I had here, this is a universal quantifier of a kind that's much higher than me just saying I'll give you small examples. And when symbolic reasoning works well, it's because you can do stuff like this. And this is very different from what we've normally done with things like discretization of continuous variables and so on. That's what I mean. So, but that interface between the two is very clunky, or you get opportunistically lucky in a few papers. And the question is it possible to do it in a much better way?
Time for one quick question if you have any. Yeah.
So you showed at the start the open cross embodiment, and you said you were going to port out some things that it doesn't do well. But I guess a more challenging question is it useful at all, or what is that useful for?
Excellent question. I think it is. At lunch, we were having a conversation with somebody about how forever we've been saying in AI that common sense is a barrier. I think what this is allowing us is all the low-level common sense that we used to worry about, the frame problem, for instance, is more or less becoming kind of solvable with this. So it gives us a basis for that sort of thing. And so the fact that if I see a plug, I should look for something else. Those kinds of things are becoming possible. And I think these big data models might actually take us to a land when we stop worrying about them to some extent. What I'm saying later on is that doesn't solve everything for you. If you get into specialist domains, you're going to have specialist concepts that don't get solved that way. But at least now you're starting from a much higher base, and then you can do new things. That's
so the arguments that you'll see, all of those kind of common sense things should appear in that case.
That's the conjecture, and I think it's beginning to happen. So all the low-level stuff about put this thing there, and if it's this, don't do this. Those kinds of things are becoming much more robust. As soon as you do anything slightly more specialized, there's no guarantees at all. And so the cloth manipulation is an example. There are things in RTX that have cables that have cloth sitting on the table. Then as soon as you say it's now flinging in the air and you have to do dynamic things, actually it doesn't perform so well and you have to do new things.
Humans seem to have common sense without ever needing to see big data, don't you think?
This is a very good philosophical question. I don't have anything clever to say that's not already been said, except of course, the poverty of stimulus argument should be taken carefully, right? So we do have a lot of early stimulus. It's presented differently and it's processed differently.
Yeah, but we don't need to see 1,000 people putting plugs in sockets to understand how plugs work.
Yeah, and I think to connecting that back to Ingmar's question, this is, I think, the most interesting AI question to me is that how did we get at these symbols and why those symbols and what's the connection? And I think that's where we are still kind of baffling.
I'm always a bit interested about the temporal aspects of the actions and tasks in general. Do you take into consideration any temporal constraints, for example, in the ultrasound scanning work, or while you're doing a learning demonstration?
So I went very quickly through this. The main thing here is that we don't know what they're searching for. So just to explain the task to everybody, people and the robot get this feed. They don't actually know the features. We're not going into a space in which the medical imaging has been solved completely. What we do know is that we got examples from people who showed us that this is how I scan. I know that later in the scan, you must be in a better place than earlier in the scan. that temporal ordering signal is actually useful, and what the machine learning model actually learns is that there must be that temporal ordering. That's what it's actually collapsing into the latent space. And so what it's learning to do is whatever you did later in a scan sequence must have been good for some reason probabilistically. So let me learn that. And that's how it learns a model of the task. So it is very much a temporal signal.
Thank you.
Cool. Let's thank the speaker.